everyone. I'm really great to be here with you in New York. I'm London-based, so it's always a nice travel here, especially a change of the weather. Um, I'm Sergei. I'm working with Kotlin and Android infrastructure at Meta. Passionate about making a developer experience great or better, depending on the circumstances I have. In the past 5 years, I'm trying to understand the world of build systems and the way to make Kotlin and Android builds faster and our developers more productive. This talk is about K2 compiler and using it in production. What it actually means is that you build your releases with this compiler and ship these releases to your users. Like, please raise your hands if you're already doing this with K2 compiler. Okay, 3 to 5% of the audience. This is great. I expected more, honestly, but I'm glad that someone might get an interesting insight from this conversation today. In the nutshell, like, should be easy, upgrade to Kotlin 2.0 and beyond, use the default language version 2.0, build, then release. That's fine. This is the algorithm. Like, at least this is what the migration guy says to us. But no, serious, like, I want to walk you through the challenges and the reasons why we started this journey almost 2-3 years ago. Meta Android code base has over 20 million lines of Kotlin code. On top of it, we have a lot of Java and native. So we use Bug2, an open source language agnostic build system. And on top of it, we have a heavily customized Kotlin compiler and Android build toolchain. It's highly optimized to have the quick turnaround in our builds and incremental iteration with code. A lot of the power of this customized compiler system gets from the compiler plugins. And originally, we started building them like 5 years ago, around the time I joined the company. And starting from lint infra, lint checks, ID integration, it all came from the compiler integration. Java compiler, then Kotlin compiler. And compiler throughput was one of the key optimizations we once landed to the language, into the infrastructure. With all this in mind, we knew that the journey to K2 would take, we thought, like a year, maybe slightly more. Ended up being 2, but we expected it to be quite long. So started around 2022, when Kotlin was probably 1.6 at that time. So time passed. When you're starting a 2-year journey at the company, you should clearly have a reason why, and the way to justify this kind of investments. So one may say that you just have to upgrade, and this is the future of the language and the ecosystem. And this is probably true, but like, this is not a selling argument in most cases. Or at least you'll get blocked at some point by the upgrade, and then you will have to do something. This is how it usually works. Another argument could be like K2-based IDE plugin, and like what JetBrains is currently working on and releasing in beta probably, should really improve the way people write code and then get inspections. It's all parallel, it's faster. This is true, and this might be one of the arguments. And the other one is the new language features, like having better optimized to provide lower level abstractions, but give you like the full control of what you're doing without any overhead. This is another. But for us, probably the biggest argument was, and the main reason was the developer productivity and the build speed. So this is the message I once sent to my manager. And this was the case when he said, okay, this is probably something, we are good, we're investing in these things. So compilation really takes a long time, especially when you're dealing with a massive code base. Like for instance, the length of this talk, like 35 to 40 minutes, is probably enough to compile a medium to large size Android application from scratch. And this is quite frustrating, especially when you need to iterate a lot, when you need to iterate with multiple versions of something, when you need to build a lot. So 2 years fast forward, now roughly 95% of the modules we ship to users for Meta application are built with K2 compiler. K2 improved the compilation process by up to 20% on average. This is our own benchmarks. And this resulted to like a better productivity and better iteration cycle for our engineers. The first apps that reached to the release were, I guess, Instagram and Threads, which happened like about 6 months ago, maybe slightly earlier. Let's have a quick history lesson and understand what overall is K2 and mainly what is K2 for like engineers, product engineers and infra engineers like us. So in the nutshell, from the outsider perspective, it's an umbrella project or set of multiple work streams that the compiler team at JetBrains were executing over the years. It all started in Kotlin 1.4 when a new type inference algorithm happened. So it dramatically changed the way we operate with types, both in our IDE and compiler. It's improved and like delivered a speed boost. Then in 1.5, they started working on the intermediate representation, the JVM IR for the backend, trying to get from the compiler that was once like very coupled with IntelliJ IDEA code base to something that is production ready, probably something that is inspired by the way LLVM is structured, LLVM compiler. Then in Kotlin 1.6, JavaScript IR happened. Then fast forward to 1.9, JVM front-end intermediate representation was introduced in beta. There were a lot of experimentation with it before, but intermediate representation is the thing that should allow us working with front-end part of the compiler as it's a very customizable and pluggable system. And then after all, Kotlin 2.0 happened, and here we are. It's time to upgrade, it's time to try it out. But not everything is this simple. But to get into more benefit that K2 is bringing us, it's important to figure out and categorize the builds that are happening in our systems. So we do different builds, and the definition of a quick one and the quick build means surprisingly different things in all these scenarios. Let's say we have a single target build. It means we have a small isolated change, probably some function body somewhere in our build graph. Then what we only need is to build this file or maybe just this function or this module where this changes. So this is why it's a single target. If we do a clean build, we rebuild the whole application. We don't have caches, like it's very, very long process usually. So to make the clean build faster, we normally need to warm up our caches, somehow deliver it from remote storage, or probably maintain the persisted storage on our machine. So kind of these things. And then finally, the incremental build, we deliver some kind of feature that changes multiple targets. Then the only thing we need is to rebuild the code we changed and then transitively rebuild the whole dependencies. Now the definition of a quick incremental build is to rebuild as few of the transitive dependencies as we can, but still maintain the quality of the build, meaning it should be still reliable and actually work, right? For today's talk, let's imagine we are building a simple app. So it has multiple dependencies. Some of them are Kotlin, some of them are not Kotlin. It has some hierarchy. App depends on bar, depends on foo, utils, library, some Java heritage, and some native code there. The easiest way to understand the impact of the throughput optimization. Throughput optimization is when you're just making your compiler faster, and thus you're getting the improvements on your overall build graph and the way you and the way you compile. So, for example, in our app we're building, if we just sequentially put in a single thread all the things we need to build, we'll get this stack of targets. So if we shrink some of them, we'll get the benefits of like building faster. Compiler throughput is an optimization that is applicable to a single compilation unit. Like in our case, let's say we are optimizing Kotlin, thus it's applicable to every blue rectangle on this diagram. So we apply optimization, then we just prettify, and just by making Kotlin C faster, we are getting the benefits in compilation time. So probably the easiest kind of the compiler throughput optimization that is available is to like imagine we generate an unreasonably large binary, because we duplicate a lot of things like images inside of it or code inside of it. Now we enable a compiler optimization that deduplicates these images or artifacts or code. This optimization itself impacts the CPU time, so it takes additional cycles to perform. However, like you will end up having a better binary, and you just do this optimization. This is just the basic example. But the other compiler throughput optimizations are like obviously K2, a new compiler, then a migration from KAPT to KSP, because the promise of KSP is the faster annotation of symbol processing. Then the Kotlin backend parallel compilation, and this is only if we take Kotlin. Unfortunately, backend parallel compilation didn't work for our cases because Bach, our build system, usually parallelized things a lot, so we were not able to get enough benefits to run it in production. But give it a try if you didn't. The promise of Kotlin symbol processing is a 2x faster builds. Try it on your project if you didn't. It works pretty smooth, especially if you want to migrate from your previously created annotation processors. However, there is the new Kotlin KSP 2 that should work with K2 compiler, and it's just in beta now. It might be a problem. Then if we look at the Kotlin backend compilation, it's all parallel compilation. It's all started in Kotlin 1.6.20, and until now it's in experimental stage. So not that many things are happening there. You can try it out with additional experimental flags, and probably experiment with the number of threads that could actively work on your backend. So it might give you a nice boost. But these are all optimizations that do not need a lot of interaction from you. So you can just try some of them on the, or partially apply it to your code base. So now let's put the compiler throughput optimization among all optimization that we can either do in a build system or for our language. So there are compiler throughput optimizations. If you apply compiler and make it go faster, you both apply it to a single target, clean build, and then incremental build, because like in any scenario, you use a compiler. So if you run the compilation avoidance, meaning you're skipping some builds when you build, you only impact the clean build and incremental build. The same is true for a critical build path optimization when you flatten the build graph, or the parallel execution when you just run multiple workers or multiple threads running parts of your builds. Finally, you can use remote execution, but it's probably the most advanced technique of parallelizing your builds, or shared indexes or shared build caches. So anyway, if you look at this classification, the only piece that impacts all the types of a build is the compiler throughput. So this is probably one of the biggest reasons why the team behind Kotlin compiler decided that it's probably the big bet and to place to like fulfill the compilation needs. Now let's dig deeper and have a look at the K2 compiler. Modern compilers are quite the complex creatures. Kotlin contains front-end, back-end, and let me call the rest like less important parts. A while ago, backend migrated to the intermediate representation. Now, front-end started working on the front-end intermediate representation. And this front-end itself is probably the biggest contributor to the compiler slowness. If we split our builds into the stages of front-end and back-end, so this is normally the picture you'll have. Like we are spending roughly 60 to 70, maybe 80% in the compilation front-end, and then we do something on the back-end. It obviously depends on the back-end you use, either JVM or JS, it could be different things. So if you look at the application we are building, so mainly what you'll get is the compilation throughput picture. Let's decouple it all, each part of the Kotlin into like a back and the front end. Front end is like red on this picture. Then group it, then apply K2. And just by shrinking this front end, because like K2 works faster, we are getting the compilation time improvements. We are not getting improvements in backend, we are not getting improvements in the way we compile native code, we only get frontend. So even if we boost the compilation of frontend like 2 times, we are not getting the overall 2 times improvement in the build time. Like early benchmarks, and it was around Kotlin 1.6 or 1.7, told us that like JetBrains benchmark, that in some cases it's possible to get a boost of 2, maybe 2.2x on builds with a nice improvement in the throughput. Like latest benchmarks on some Android apps, however, show slightly different picture. It's still like a good improvement. It's mainly an improvement in code analysis. So there are links in my presentation. You can check the official benchmarks. When we started, the overall expectation would be to eventually get at least like 10% improvements for our build. It would be already a good use of our time and a solid improvement in developer productivity. For a long time, on our workloads, it was not possible to compare apples to apples like K1 and K2, mainly because like the reliability of K2 was not on par with K1. ABI stability was not there, so meaning in between various night builds, even the ABI could change, so your caches would be like totally invalidated. And then core infra, KPT and KSP, for quite a long time, they were only K1 based. These days, the situation is slightly more like apples to apples comparisons. The only part of the infrastructure that is actively in beta, is not unstable, is KSP2. KSP2 is the new API for KSP. That is a simple processor. It's quite a big step for KSP as a tool. However, the migration is not that dramatically complicated as we initially thought it would be. So try it out if you hadn't. So we started our journey with Kotlin 1.6. It was quite a long time ago. At that time, even there was the use FIR flag. There were probably no public name of K2. However, someone might correct me if I'm wrong. So we started experimenting, and we were barely able to build a small project at that time. So we started with Hello World, then we tried to add some libraries that we have, and this was probably the borderline of what was available that day. We relied on the compiler plugin API. Our build system bug was not ready, so sometimes we were calling the gradle command from CLI just to make it work. And front-end plugins infrastructure required a complete rewrite on our side. We were quite upset, but energized to keep going. In 6 months, on early Kotlin 1.7 builds, we were finally able to build something, like something real. At that time, JetBrains changed the flag, so use K2 was introduced. It was much nicer. Now it's not FIR. We adopted a new compiler plugin infrastructure. And at the same time, we started pushing some of our compiler plugins to open source just to share it and make sure like people see how we develop it and we get a better feedback loop. The first plugin we introduced was data class generate. The plugin itself heavily improves the application size, and especially when it gets to quotes. The only thing it does, it manages the way data classes are stored in DEX codes. By removing unnecessary method, that there's a lot of method in Kotlin data classes that people don't usually use. So the goal of data class generate is to detect them and remove from the resulting binaries, or probably compress some of the identical data classes there. So we updated it to K2. There were like a lot of problems at that time, mainly due to inconsistencies between K1 and K2 APIs. So there were several methods that were used both in K1 and K2 API. Some of the fields here and there returned null just because they were linked abstraction. But in defense, there were like literally no documentation at that time, and also this API was never recommended. It's still not recommended, so we used it at our own risk. But finally, we migrated it, it works. Then 6 more months later, probably slightly more, Kotlin 1.7 started. We had a lot of progress, especially with the compilation reliability. At the time, we first realized that probably we can enable K2 builds for our developers. And we led people around the company to build something with K2, report bugs, try it out, and help us move it faster. We introduced the shadow jobs for K1 to K2 in CI that really brought a lot of context. And we started seeing like how different these compilers behave, even though they meant to compile the same code, and K2 didn't introduce any new language features at the moment. On the compiler plugins front, binding context was that. Type slicing that we usually used in the past to get some information about interfaces or annotation that we needed, gone. And we needed to migrate everything to FIR, which was quite an interesting exercise. Some of the API methods returned null and did it inconsistently for binding context. So binding context itself is kind of a map of your program structure, your types, probably some expression there. It still existed in some references, but not in the others. So in compiler backend, it was somewhat possible to use it. But now the whole point was to start using FIR session and checker context in as many cases as it's possible. And it was a big change for us. So probably like 1 or 2 years ago, I was desperate about getting some help of like how to do the migration of K1 to K2 plugin. I even got to Stack Overflow, but like everyone ghosted me there. And I was just trying to get the idea of like how to share data in between various layers of the compiler. I later asked in Slack and people were able to help me, so use Slack. But the problem there is how to collect all existing types based on some condition, record it somewhere, and then use it at a later stage. Probably you just need to write it to a JSON file. This is something we needed to improve the build system experience. But in K1, it was all possible by using just analysis extension. So the mitigation we came with at that moment was to use a FIR checker to collect data. Then to use an instance called service in K2 compiler and API, and like the data structure we pass to both FIR on front end and IR on the back end. And use the IR generation extension that also process something when all the checkers are done. So the problem with checkers, and like checker is something, for example, that could provide a length check for you, or check that you like synthetically corrected, you wrote something synthetically correct in the language. The problem is that there is no deterministic way to say which checker will happen before each other. So you cannot output data from this checker. So you need to find out the later process that could do it for you and collect everything in checkers. So this is how it effectively looked like. We extended a surveys field by the delegation in a FIR session. So we did it all statically. We injected these methods. And then at the point where we were creating surveys, we like use FIR extension session components to pass the session there and then create a factory of what we are doing. Later in the checker, we were just recording stuff in the context that we had, and we used these surveys. And finally, we all registered it all together. So there was a K1 implementation and K2 implementation. We combined them and registered both. So luckily at that time, only one of them were used. So depending on the flag, either K2 implementation or K1 implementation. But the problem was solvable, even at that time. Now the API is much better, I would say. At the same time, the Kotlin 1.7 came, and it also brought a nice improvement in the language, and everything became faster, probably around 10% on average, as we noticed it at that time. Another 6 months passed. Kotlin 1.8, language version 2.0. Finally, JetBrains figure out how to name this flag, and for the good this time. K2 is maturing. KAPT and KSP works still by default with K1. It's fine. It's not giving you as much of the build improvement as you want, but the things are good. And the significant part of the compiler API is already deprecated, meaning we can navigate the code with confidence and ship things without like having to worry about the deprecation going forward. Probably the most severe compiler bug that we had at the moment, which happened in 1.8 something, was that it was possible to import something that doesn't exist in compiler. So for example, this thing that doesn't exist, like an import, like you put anything there and then compiler was saying, okay, I can compile this code. K1 was like screaming obviously, but K2 did it. It like took quite a long time to recover for us. And then a big part of Android X was moving together with Kotlin. It depended on Kotlin compiler. And one of the good examples there is Android Lint that were shipping with UAST at that moment that depended already on Java 17. So we wanted to make linting framework work for us, but there was a surprise. All the Android was X that depended on the compiler was shipping with Java 17 and the bytecode version 61 at the time. So we had to take a deep breath and ship Java 17 support for everywhere in our ecosystem, which took probably another 3 to 4 months, was quite an exercise. We were really worried like how much time it would take us, but finally we started using it. Java 17, like probably by surprise, brought us another nice win in developer builds, but for Java this time. In Kotlin 1.8, we created the migration plugin for modules where we wanted to run both K1 and K2 for quite a while. So the role of this plugin was to, in some cases, make K2 more stupid, so not to perform any nice, new, shiny smart casts, and also to like reduce the impact of some bugs that K2 has. But in addition to this, we made K1 more restrictive in several cases. That the only thing we wanted is to K1 and K2 behave almost the same despite the bugs and instability in between them. We supported multiple versions of compiler in lints, then adopted it all in like everywhere in our infrastructure. It worked quite nice until the day when we started shipping Kotlin 2.0. Then it's all just became redundant. We even decided not to open source it. Then finally Kotlin 1.9 and 1.2. It's still language version 2.0. Nice, we didn't have to change it this time. K2 goes to JVM beta and then to stable, meaning we kind of have a stable compiler now, and now JetBrains and other contributors could iterate on the new language features instead of stabilizing the compiler, which should give us more benefits. We are kicking off K2 versus K1 build time comparison on a regular basis, especially when new targets apply the K2 compiler there. And now we are already running K2 meta-wide on like probably all of our major applications, which was like a big win for the developer productivity. For the takeaways, K2 and Kotlin 2.0 is a new default, like use it, upgrade, it's nice, sometimes scary, but nice. Let's celebrate. On average, we have our builds running faster. If you're using the custom compiler plugins, go migrate them. It will take time. There's a lack of documentation there, but it's all manageable, especially if you're using large language models now that could like process the whole code of the Kotlin compiler and make it easier for you. Try KSP2 and move away from KPT. This all will give us a better productivity, especially with your builds. Thank you. Time for questions.